Welcome to today's Explainer. We're going to explore something that operates quietly behind the scenes, but absolutely powers almost every major company you interact with. To put things into perspective, your average enterprise today is generating terabytes, sometimes even petabytes of data every single day. That is a mind-boggling amount of information. So we're going to see exactly how massive modern enterprises extract immense, tangible value from what is otherwise just an overwhelming, chaotic mountain of raw data.
Okay, let's dive into this. Have you ever really stopped to wonder how global enterprises turn decades of messy, totally disjointed data into million-dollar decisions? It's a massive, high-stakes industrial problem. If a company can't make sense of its own history, it simply cannot navigate its future in a hyper-competitive market.
So here is the roadmap for our data-to-decision journey today. Number 1, the data warehouse defined. 2, schemas and architecture. 3, types of analytics. 4, decision support in KDD. And finally, number 5, real-world applications.
All right, Section 1, the data warehouse defined, or building the corporate foundation.
So what exactly is a data warehouse? Simply put, it's a centralized, consolidated computing repository. But here's the absolute key distinction we have to make. It is built specifically for analytical queries over historical enterprise data, rather than day-to-day transactions. Think of it like a massive, hyper-organized physical distribution center for corporate history. Your standard, everyday transaction databases, like the system that records a single credit card swipe at a grocery store register, those are fantastic for super quick, single-row tasks. But they are absolutely not built to find long-term trends. The data warehouse steps in to consolidate all of that chaotic, real-time operational data into one incredibly clean, permanent archive.
Data warehousing pioneer W.H. Inman actually laid out 4 fundamental traits that define this foundation perfectly, and honestly, it's a brilliant engineering solution. First, it's subject-oriented. This means it's organized around core business domains, like sales or inventory, rather than just individual software applications. Second, it's integrated. Data is merged from completely heterogeneous, messy sources into a single, unified schema. Third, it's time-variant. Every single record is stamped with a time dimension, so data scientists can look back over 5 or 10 years to spot long-term trends. And fourth, it's non-volatile. You can think of this as the ultimate no-take-backs rule of corporate history. Data is loaded incrementally and is strictly read-only. Once it enters the warehouse, it isn't modified and it's definitely not deleted, which ensures a perfectly consistent historical baseline.
Which brings us to Section 2, schemas and architecture, or structuring the chaos.
Now, what's really interesting is the star schema architecture. Think of the literal shape of a star. Right at the center, you have what's called the fact table. This contains measurable metrics, stuff like total revenue or total units sold. This center is surrounded radially by what we call dimension tables, which hold descriptive attributes like the store location or the product category. Because these dimension tables are denormalized, which just means they deliberately allow some repetitive data, they maximize query read performance. It's incredibly fast because the database engine doesn't have to jump through a bunch of relational hoops to fetch the answers.
But in engineering, there are always trade-offs, right? Let's contrast that star schema with the snowflake schema. You can think of the star schema like throwing all your clothes into one giant, super easy-to-reach closet. It boasts very fast query processing, but at the cost of some redundancy and messiness. The snowflake schema, on the other hand, takes a totally different path. It completely normalizes those dimension tables into secondary lookup subtables, stripping out the redundancy to reach what's called the third normal form. Think of this like a hyper-organized filing cabinet where you literally have to open 3 different drawers just to find a specific pair of socks. It makes the snowflake incredibly storage efficient, saving massive amounts of disk space. But because the data is broken up into so many tiny interconnected tables, the database has to execute really complex joins, and that means slower analytical queries. So it's your classic choice between pure query speed and optimal storage efficiency.
Let's move on to Section 3. Types of analytics, or processing the data.
To actually process all this warehouse data, enterprises rely on OLAP, which stands for Online Analytical Processing. These are specialized technologies enabling fast, interactive, multidimensional analysis of those consolidated corporate records. So how does OLAP differ from your basic transactional systems? Well, instead of processing frequent single-row writes, like depositing $20 into your bank account, OLAP is built to scan literally millions of rows simultaneously to calculate aggregate trends. It processes massive, complex, read-heavy queries to give executives the big picture.
We can kind of think about the different architectures for OLAP using the Goldilocks method. First, you have MOLAP, or multidimensional OLAP. It pre-calculates and stores data in proprietary multidimensional cubes. Now, this is exceptionally fast, but it struggles with really deep, granular data. It's a bit too rigid. You could say it's a bit too hot. Then you have ROLAP, or relational OLAP. It keeps data in standard relational tables and executes dynamic SQL. It is highly scalable and handles massive amounts of detail, but it can be a bit slow for instant dashboard loads, so a little too cold. And then we have HOLAP, the hybrid OLAP. This is the just right solution. It uses those fast multidimensional cubes for high-level summaries, while still retaining standard relational tables for the raw, granular details. It brilliantly balances speed and depth.
Section 4. Decision Support and KDD, moving from analytics to knowledge.
So how do executives actually interact with all this data? They use a decision support system, or DSS for short. A DSS relies on 3 core components. There's a data management subsystem to access that pristine warehouse data, a model management subsystem equipped with mathematical models, and a user interface subsystem featuring highly visual dashboards. The absolutely crucial point here, the real industrial value, is that a DSS allows non-technical business managers to run strategic what-if simulations, like dynamically projecting how a 15% increase in fuel costs will impact next year's logistics margins. And they can do all of this without writing a single line of code.
But wait, to actually generate the insights powering those dashboards, data scientists use a highly formal pipeline called KDD, or Knowledge Discovery in Databases. It's a rigorous 7-step process: data cleaning, integration, selection, transformation, data mining, pattern evaluation, and finally, knowledge presentation. People love to use data mining as a catch-all buzzword. It gets all the PR and all the glory. But as this pipeline shows us, data mining is actually just step 5. It's merely one specialized algorithmic phase within a much broader pipeline. Steps 1 through 4, especially data cleaning, is where the real tedious engineering elbow grease happens to turn raw data into actionable knowledge. Now, within that 5th data mining step, the algorithms generally fall into 2 main paradigms. You've got predictive algorithms, like classification and regression, which analyze historical training data to forecast unknown or future outcomes. They're essentially trying to predict what will happen. On the flip side, you have descriptive algorithms, like clustering and association rule mining. These explore datasets to reveal hidden structures and affinities without any predefined target variables. So they aren't forecasting the future. They're actually mapping the existing hidden relationships that are already present in your data.
Section 5. Real-world applications. The industrial impact. And this brilliantly illustrates why all of this matters. Let's ground this architecture in the tangible impact it has on our everyday lives.
Take banking and fraud detection, for example. Every single day, retail banks are handling literally millions of credit card transactions. By feeding data from their warehouses into predictive classification and anomaly detection models, they establish a behavioral baseline for you. The moment a transaction deviates from that baseline, say you buy a coffee in Chicago and 10 minutes later someone tries to buy a laptop in London, the algorithm instantly flags the deviation. It automatically locks the account, utilizing those lightning-fast queries to save millions of dollars and protect consumers before they even realize they're at risk.
But the impact in healthcare, particularly oncology, is truly profound. Medical institutions use descriptive clustering algorithms to deeply analyze massive electronic health records directly from their data warehouses. By comparing specific tumor genetic mutations with years of historical treatment outcomes, doctors can use data mining to craft highly personalized chemotherapy or immunotherapy plans based strictly on a patient's unique genetic profile. Make no mistake about it, the data warehouse is directly improving survival rates. It is quite literally saving lives.
Even day-to-day hospital logistics benefit immensely from this. By applying predictive regression models to historical warehouse data, hospital administrators can analyze patient admission trends to accurately forecast daily emergency room traffic. Remember those what-if scenarios we talked about with the DSS? This is exactly the kind of simulation administrators run on their visual dashboards. This forecasting allows them to optimize bed allocations, proactively identify patients at risk for readmission, and ensure that nurse staffing schedules perfectly match the projected patient volume. It transforms raw, historical records into a tangible, very real human benefit.
Which leads us to a final, kind of provocative thought to wrap up. Every swipe, every click, every single digital interaction you make today is currently being extracted, transformed, and loaded into an enterprise repository somewhere.
So what hidden patterns is your daily digital footprint building in the data warehouses of tomorrow? Thank you so much for joining me on today's Explainer. Keep questioning the data around you, and we'll see you next time.